Good afternoon and welcome. On the 1st of February this year, we appointed a new professor at the Department of Wind Energy, namely a professor in offshore wind power integration. And the person in question was Nicolaos Cutululis, which stands here. Nicolaos has been with us since about 2005, and in those years have come with a background in control of hybrid system, but has during those years grown this area on offshore grid integration to becoming an important field at the department. And I would be very, very much surprised if we wouldn't hear more about this topic here today. So today we celebrate our new professor, and we also proudly present him to you, colleagues, friends, family. So without more from me, I give you Nicolaos Cutululis.
Thank you, Peter, and good afternoon, everybody. Actually, just seeing Henry coming in, I realized that in the last 3 months we had one inaugural lecture every month. Now it was August, September, and now October. So I start suspecting that Peter likes the catering here in Vindeby, that they do that every month. So yeah, I am October man in that sense. So thank you, everybody, and thank you very much for joining me in this special moment for me. I think this day with many firsts. It's actually the first time I'm going to give a lecture in front of my family, both here in the room, but also present online. So that's new. It's also actually the very first time I actually speak in this room. I've been here several times, but never speaking, most of the time listening to others. And it's, of course, the first time I'm going to give an inaugural lecture. So many firsts for me today. So I was, how not to get a little emotional on that sense, and I sort of, trust me, I know what emotional is with my Balkans meet South Europe heritage. It's a little easy, my mother, of course, started crying a lot when she heard about the position. She's probably crying right now watching from Greece. Yes, Mama? And yeah, I guess even my friend's mother started crying when she heard about it. So, of course, I get a little worried. Maybe I get a little too emotional today, but then I talked to my wife and she said, stop it, don't worry, you only cry at movies, and yeah, that's true. And sometimes maybe after some meetings with the management, but she doesn't know that, and it's okay. She told me, don't worry, actually the only thing you should do is make sure you don't make anyone else cry today. So my main objective for today with my presentation is not make anyone cry, but also, maybe have a little fun doing it, and not least, maybe tell you a few things about offshore wind integration and why we are doing this and why we think this is, from where I stand, the most important thing in the world, So, integrating offshore wind. Well, I will try to talk to you in the next, hopefully 45 minutes or so, is sort of tell you why is this even a thing, then what we are doing and how, who we are doing it, and what is next, what we are planning to do next on that. So why? Well, I think the why is maybe not very difficult to say. It's because it's wind and because we are in Denmark, and whatever has to do with wind, Denmark is a leader. But actually in offshore wind, Denmark is an absolute leader, because we had the first ever offshore wind farm, Vindeby, was built in 1991, was in Denmark, was also the first offshore wind farm to be decommissioned, also in Denmark in 2017, but also the large scale, or the development of offshore wind, started in Denmark with Hornsrev 1 wind farm in 2002 and Newstead 1 in 2003, both of them the first large scale, so over hundreds of megawatts being installed. And also, I think one important reason that we do research in offshore wind in Denmark is because Denmark is also home to the most shown picture ever in offshore wind. Can you hear me? That's okay. So I'm sure that all of you in this room, or most of you, have seen this picture, which is the same Holzrev 1 wind farm, and it's yeah, it's not only spectacular. I think it looks very nice, but it actually also shows how complex the interaction between the wind turbines in a wind farm are. Yeah, this picture was taken in, if I remember correctly, in early morning with very special weather conditions with a lot of humidity, and we can actually see. I mean, actually, literally, there were research areas that started from this picture, like wind farm control, in sense of doing the aerodynamic interaction between the wind turbines, and you can see in the picture very clearly how the wakes from one wind, with the front row wind turbines, are impacting the one behind them. And you can even see that one of the principles of control here, when this one seems to be a little misaligned and the wake behind it is redirected towards away from the other wind turbines. So this is one of the big areas that do research, and people all over the world are joking that we are doing research in offshore wind to be able to show this picture. Even I managed to sneak it in from the very beginning, but we did some work here. I'm not going to show it again here, because I think the second part is that there is like a tacit agreement that you show it only once in a presentation. We're not abused with that. So one of the reasons I think offshore wind is interesting. It's also because of the very nice visuals, and here is the same picture from Holzrev 2. It's maybe not as spectacular as the previous one because it's a little further away, but I think it's also very nice. And I think, as I said, one of the main characteristics of offshore wind is that it is very visual. And in today's world, I think being visual is one big step ahead. But yeah, this is, as you can imagine, this is not really why we do research in offshore wind. I think why we do that, if I can paraphrase one of the legends, Henrik Stiesdal used that in his inspiring lecture at RISO some years ago. I think we do that because that is where the money is. And I think today offshore wind is in many ways big and costly, and this is, of course, the perfect environment to do research and innovation, trying to increase the performance and lowering the cost. Now, when we say offshore wind is big, as I said, Mr. August, I think, used this picture in his presentation, Henrik, showing a few years ago about a comparison, trying to show how big the wind turbines have become today. And you can see, going from the Vindeby, the wind farm I was telling you about, the first offshore wind farm in the world, moving to one of the large offshore wind farms in UK, Barbobank extension. You can see that it sort of took us, moving from 0.5 megawatt to 8 megawatts, probably took around, this is a few years ago, so it took, what, 20, 25 years to go to these sizes. But I actually think that this was not really the best picture to show that, because you can see we are still comparing the wind turbines to an airplane, trying to give a context to the size of that. But I think even if it took us, as I said, 25 years to go to 8 megawatts, going to 12 megawatts, or going 50% more than that, it took us only 3-4 years. And today already, the largest offshore wind turbine in the world is the GE one, 12 megawatts, which is erected as we speak. I'm not sure if it's already up and running, or they're still building the prototype in Netherlands, but it's been already announced that it's going to be used in a number of very large offshore projects that are coming up. So offshore wind turbines have become very, very, very large machines, and today, actually, I think trying to compare them to an airplane is very obsolete, because unfortunately for the airplanes, they've become much smaller than the wind turbines. So today, the way to look at the wind turbines is put them in between real large constructions and landmarks constructions in the world, like the Eiffel Tower or the Empire State Building, with a very important difference that those two buildings are not actually dynamic machines, rotating machines. They are just sitting structures. So offshore wind is very, very large in terms of wind turbines. But then also I was thinking, how large is a large wind farm? And I don't know, maybe some of you have looked at that, but I hadn't really do that. And yes, you can see the numbers here. It's a very large number of wind turbines, 174, a very large capacity. I mean, come on, wow, 1.2 gigawatts already. We have an offshore wind power plant in the gigawatt scale, and this is the Hornsea Project 1, the largest offshore wind farm in the world. But actually what I wanted to tell you about in this moment was the size of it, that it actually covers an area of 407 square kilometers. And you know, it's not always easy to understand what that means. So I try to find, to compare it to something, to give it some context around it. And of course, I started with the DTU Ljungby campus. Sorry, that's not even close. It's, if I'm not very wrong, that's around 1 square kilometer. So it's a very, very, very small part. So then, of course, I moved up and tried to compare it to Roskilde, yeah, our city where our campus is at Riso. That's still not good enough, or it's roughly half the size of an offshore wind farm, and keep going up until I ended up with Aarhus, which is a little larger. It covers a little larger area than an offshore wind farm. At least that's according to Wikipedia. But I think it's fairly impressive to think that an offshore wind farm today covers an area which is the same size as the second largest city in Denmark. Yes, Denmark is a small country, but still, this is the second largest city in Denmark. So offshore wind farm is, offshore wind in general is very large, not only in sense of a single machines, but also as projects, they are very large. So where are we today in terms of offshore wind? I don't think we are very, very far away. We have I think around 18 gigawatts of installed capacity, and this is not spectacularly large. I think it's a little more than what Denmark has as a country installed capacity, and it's pretty much all of it, or the 18 gigawatts that you see here installed in Europe represent around 85% of the total capacity, because offshore wind is still fairly local. When we talk about offshore wind, we don't really talk about different areas than the northern seas, yeah, and mostly the North Sea. But then this thing is changing, because if we look a little more detail in the top offshore markets in 2018, of course you see that China has started installing offshore wind, and I think, talking about China, this is only demonstration kind of projects. They haven't really started the big development, and of course they're going to skew all the numbers once they start the development. But I think the message here is that offshore wind is moving from something rather local and still rather small in terms of installed capacity to becoming global and increasing the numbers very much. And you probably have heard about all the big plants and the projects that are already starting in US and Asia, in Taiwan, and I think everybody expects that in 5-10 years at least half of the world market on offshore wind will be in Asia. So I think we are, as I said, we are at the beginning of the development of offshore wind, and this is, you know, one of the estimations where are we aiming at, or where are we going at. And like any estimation, you probably know, is probably wrong. Yeah, all of them are more or less wrong. It's like the models, they are all of them wrong, but some of them are useful. And I think this one gives a little, from Irina, gives a little sense where people are expecting offshore wind to go by 2050, and they expect from the roughly 20 gigawatts that we have today to get to 520 gigawatts, and that it's already a sizable amount of installed capacity, and I think it represents roughly half of the total electricity installed capacity in Europe today. So the expectations and the ambitions for offshore wind I think are fairly large. How do we get there? Or even how did we get here? And then how do we get to 520 gigawatts? So I think basically the main thing that, like all things that we are trying to do, is related to cost reduction, but that's even more when it comes to offshore wind, because I think one of the saying is that whatever you do, once you move offshore, it's 3-5 times more expensive. And I think offshore wind, the cost, the LCOE from offshore wind has decreased a lot. Maybe some of you have seen that graph with some projections, how the price will develop over time, and then immediately that was completely wrong. I think the reality went against that very far, and you see already there was a big drop in the last few years in the cost of offshore wind, and this is expected to continue for a while. But if you look a little deeper into that, this cost reduction is mainly coming from technology innovations in turbines, what I was showing earlier. So the huge increase in turbine sizes drove the cost down, and also some innovations in installations when they are installing it, but also reduction in financing costs. So that's from my side when I'm talking about integrating wind. So from the more electrical or power system perspective, that says that our side has not contributed much to that. And this is also obvious. I saw this earlier this year and actually made my life easier, because I've been trying to say that before, but I never had a graph to show it. And now I have it. This is for some of the last projects that you see in the different countries. This is the LCOE development, but you can also see with yellow is the cost of the grid connection, how much it actually costed not only to build the wind farm, but to build the infrastructure we need to take the power to the shore. And you can see that the cost of grid connection hasn't really decreased, or the contrary, it has a tendency to increase because the distances from shore are increasing. And of course, it's simply longer distance to move the electricity to shore. And you can have the same wind turbines or even fewer wind turbines that you need to put out there because the size have increased, but still you have that amount of power or even higher that you need to move to shore. So I think from my perspective, in terms of cost reduction on offshore wind, the part for the electrical side, it's more or less just starting. Now, what we are doing in this sense, I think that this pretty much shows very well, you know, the main drivers for our research. We are a more applied kind of department doing applied research, and we are trying to always have in mind when we are doing our research to look at the drivers, cost of energy, system value, and sustainability. And sustainability, maybe we do some things there. I'm not very clear about it, but at least when we talk about cost of energy and system value, those are definitely drivers for our research, and there are things that we are doing that have a very clear impact into that. And yeah, if it's not always easy, but if I try to give a structure to the research we are doing in offshore wind integration, I came up with 3 main areas. One is electrical infrastructure design and optimization. The second one is working on wind power plants operation and control, and I think both of them are also related to of course the cost, but also the performance and the system value. And the third area is looking at offshore transmission, grids, and integration. So yeah, remember my objective is not anyone to cry today, so I will just try to give a couple of very simple examples of the work we are doing in these areas, and hopefully give you a flavor of the work we are doing. So, starting with electrical infrastructure design and optimization. I really love this GIF, so I cannot stop watching that. So in this area, what we are trying to do is basically optimize the wind farm collection systems or the electrical connection to shore. And why we are doing that? Because this is actually representing only the electrical infrastructure inside the wind farm without the grid connection. It can represent a sizable part of the total cost of the projects, of the offshore projects. But also because we're going to install a lot of cables in the North Sea and all the seas when we are installing wind power. According to one estimate, only in UK in the next decade they are expecting to install around 19,000 kilometers of cables for collection system. Yeah, 19,000, that's almost halfway around the globe. So if we are able to reduce some of the costs here, the impact should be visible. So what is the problem here? In a very simple way, what we are trying to do is optimally join these points. And of course, all of you know that when you say optimally do something, this is a very quickly, this is becoming a big area. What is optimality and how do we define it here? But a wind farm, a modern large offshore wind farm, may look a little like that, not exactly like that. This is an obvious synthetic case, the way the wind turbines are placed there. I see already some of the colleagues working with wind turbine locations that this is not correct. Yes, I know it's not correct, it's just an example, but we are trying to see that there are many wind turbines that you are trying to install. Then you also, most of the time, have some areas for whatever reasons, they are called forbidden areas. You cannot install wind turbines there, or you cannot have your cables crossing and things like like that. And then you can have a number of substations that you can connect the power to the shore. And then, of course, you are trying to find the optimal way to do that. And the way to do that, I think there are different ways of doing that. One is heuristics. The other one was the meta-heuristics, but after the September presentation of Matthias with fluke optimization, I decided to skip the meta-heuristics. He's not here today, but so what we are trying to do is actually go to mathematics and try to develop a mixed MILP kind of problem, and that's the objective most of the time is to try to minimize the total cost. So you are trying to minimize the capital expenses, so basically the length of cables that you are putting, but also try to minimize the losses, which are pretty much the operational part that it's related only to the cables part of the offshore wind farm. And then, of course, this is the objective, and then we have a very large number of constraints or things that have to be taken into account, which I'm not going to go into details, but there are a lot of issues that are coming from practicalities. How many wind turbines you can connect to an offshore wind farm, how many wind turbines can be on a given cable with a given cross section, and so on. Even rather simple ones that each wind turbine needs to be connected to the shore. You should not leave a wind turbine that is not connected, and so on. So after defining all those constraints, yeah, you will try to start try and run the model that you will get. But this will not take us very far, because it might work for smaller instances, but when you're talking about large offshore wind farms with tens and hundreds of wind turbines, the nature of the problem is such that will very quickly become very large. So just trying to run all the to do all the computations, it's not going to work. So then what we have to do is try to find a clever way to do the search, and this is the way we are doing it here, is by having an iterative process where we start with a smaller instance to try to find a visibility problem. So try to find a relaxed version of the problem, and then after that use this as a warm startup for the next iteration, which will try to search on a little larger domain, and so on, and find the next iteration, and so on, until we find the next iteration, and if you are lucky in the fourth one, you have found the same point, and then you say that this is the global minimum, so we stop our search, and that means that we have reduced the domain that we have to search. Of course, this is a heuristic, and I'm sure, of course, I would show a successful example here, yeah, but I'm sure that some of you can tell me very quickly what would have happened or what we need to do to get an unsuccessful case. Anyone? No? I was hoping to activate a large classroom so I can put it in my UDTU project. But anyway, of course, it depends the size of the iteration, the size of the domain that you can use in each iteration. If this was smaller and you will still hit here, you will still find this and consider this a global minimum, and then we will end up in a place which is not a global minimum, of course. So this is the heuristic part, but by doing that we have managed to reduce the computational time, and of course we were very happy. But then in order to publish that, we need to explain or to show how better we are, or how we compare to other solutions. And this is the results from a benchmarking that we did a number of offshore wind farms here from Hornsrev 1. Remember the first large offshore wind farm in Denmark, going to the ones in UK, Thanet, and even the London Array, the very large instance offshore wind farm with 174, I think, or 75 wind turbines. So what we try to do here is to solve the same problem and compare our results in terms of optimality gap and computational time to what is widely considered the best or the state-of-the-art literature approach. As you can see, I think we are most of the time doing as good as that method, or even better, with few exceptions. So that, of course, is very exciting and gave for a very, 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 very happy group of people. So we think that that this is a nice way to do that, and we have continued working in this, and we have extended the algorithm to actually include the forbidden zones, because it didn't really include in that benchmark. We were trying to compare with what is in the literature, so we didn't include it, but also try to be able to choose when you have different positions or locations for offshore substations, try to find the best ones. And you can see that this graph sort of shows a little what would be the answer compared to the very initial one which I started, where I was trying to define the problem. So by doing that, I think this is one of the areas that we are doing research, and I think it's one of the areas, like Matthias said also, in general, in optimization in wind energy, is one of the areas that will become more and more important in the future. Now, moving on to wind power plants operation and control. Here, the example I want to bring here is about how we control these very large offshore wind power plants. Some of them connected via HVDC grids, so having transform the power to DC and then move to the shore, and how we can improve their performance through control. So the issue here is you have this setup where we have the onshore grid. We have the onshore grid here, and then we have the DC connection to shore, and then you have a cluster of wind farms. This can be a large one, can be 800 megawatts, and can be 1, 2, 3 different wind farms, and they can typically be owned by different developers, so they will have different ways of controlling them, or they will have their own wind farm control. And the exercise here, or the objective here, is to develop a reactive power voltage control that will improve the performance of the whole cluster, instead of trying to optimize the individual wind farms. And there are different methods that were tested here. I'm only going to talk or try to show some results for the coordinated voltage control scheme. And the point here was trying to see how you can control voltage. Is a very local thing. So it's not like frequency, which is a global indicator, but it can be very local. And the objective here is to see how we can control the voltage in the wind farm, so the result will be best for the whole wind farm. And the idea is to try to use a pilot bus. Is a concept which is being used in the AC systems, and we are using that in offshore. So we choose that pilot bus, and then we try to control the voltage at that pilot bus with different objectives. So in steady state control, the idea is you try to minimize the losses in the whole wind farm. So it's another way of doing it dynamically. What I was talking before was more in the design phase, where you design the layout of the wind farm, trying to have the minimum level of losses. But then you also have losses when you operate. Of course, you cannot avoid losses, so you can operate it in a way that you can minimize these losses. And then, of course, in a dynamic state, to see if by using one voltage profile, if you can help the different transients that can happen in the cluster to perform better. So what we did for the steady state control, as I said, we are trying to maintain the voltage of the pilot bus, and this indirectly trying to maintain the voltage in the whole wind farm. And the way to do that is by defining what would be the optimal reference voltage for the pilot bus, such that we minimize the losses. And you can see here we have the voltage at the pilot bus, function of the losses inside the whole wind farm. And you have that, of course, the losses depend on the power production level, so you have that for the different levels. And then what we are basically trying to do is to maintain the voltage at the pilot bus to the value that brings the lowest part of each of these curves. And how we do that? Simple. It's not very complicated. Again, I'm not gonna insist on that. Just trying to show that it's not extremely trivial how you do that. There are different stages and different ways to do that, both for steady state and dynamic control. So by doing that, I'll jump directly to the results. You can see that we managed to reduce the losses by 6% because you maintain the voltage, you indirectly maintain the voltage at the optimum level in the whole cluster. But we are also, by distributing the reactive power set points smarter or better, we can reduce the voltages seen by each wind turbine. And typically, the last wind turbines on the string, they see over voltages, and that over voltages are now reduced by distributing the power set points. So by trying to control the whole cluster and not the individual wind farms or individual wind turbines, we think we can at the end of the day also sort of reduce the cost of energy, because you are reducing the losses and you are increasing the performance of the offshore wind farm. And of course, by utilizing your reactive power margin better also means that the voltage stability margin of the offshore AC grid is improved with the proposed method. So yeah, this is good results. Now, the final part that I wanted to talk about is we do all those things. We design the wind farm, we design different controllers for them, trying to control them in the best way, but sooner or later we need to move this power to the shore. And when we talk about the offshore transmission, the way of connecting offshore wind farms, there are basically two ways of connecting offshore wind farms to the shore. One is the standard way through AC connection, so the whole idea is to try to get all the electricity produced here and bring it to the main onshore network. And to do that, we are typically increasing the voltage levels in the different parts simply to reduce the losses. So you have a voltage level inside the wind farm, then this is stepped up with the offshore AC substation and then brought to the shore. And this works very fine. Most of the offshore wind farms are using that today if the distances from shore are within a certain level. But if we are moving further away from the shore, and this is happening more and more today, then at some point AC transmission it's not good enough. We cannot use it anymore. So in this sense, then we have to use DC transmission, and this is very similar to the previous one, except that we have this offshore converter station which is transforming the power to DC and then moving it to shore, and then of course here you have to convert it back to AC and feed it into the AC system. So these are the main ways of transporting the power to the shore. And you would expect that we already know what is the best solution for which case right now. Actually, I think it's very far from clear today. We have, as I said, a lot of offshore wind farms that have this connection, and this is actually Hornsrev 1, and you see the cable to shore, and the Hornsrev 2 and 3, how they move to shore, but all of them are very close to shore. Then you have a big number of offshore wind farms, mostly in Germany, where you have this HVDC connected, which are connected through the second way I showed you before, through DC to shore, and their distance is fairly large. I think all of them are more than 130 kilometers for shore, and this is the second one. But then we also have all kind of other options. We have the high voltage with compensation, and this is the Hornsea, the offshore wind farm, the largest in the world I showed you earlier, which even if it has 120 kilometers from shore, they did not choose the HVDC connection, but they choose to have a midpoint compensation, so split that in two AC connections and bring it to shore. And the most interesting of all, we have the combined solution of Krüger's Flak between Denmark and Germany, where you actually have an AC interconnection almost all the way, but because this is also connecting two power systems that have different synchronous area, so they have different frequency, then you need to break the frequency at some point to be able to connect them. And then you have a back-to-back converter here on the shore in Germany. And to make things, so this is actually the first project in the world that is combining an interconnector and transmission from offshore wind farms. And to make things even more interesting, the voltage levels is different. I think it's 220 kV in the Danish side and 150 kV on the German side. And I think this whole setup is very, very interesting. We have a friend and colleague from Belgium that keeps saying that people will be talking about this connection in the the different conference for decades to come and learn from this connection. So I think it's very interesting, but I think it also shows that we are still looking for the best way to connect to the shore. And then, of course, everybody is expecting that if we have the development that we are expecting from the offshore wind, then sooner or later we will end up having so much infrastructure out there that it will make sense to make a meshed grid. And a meshed grid means that the power from getting to one point to another has more than one route to go there. So it's very much like the AC system onshore today. So we can expect to see something like that, meshed grids, or even build some artificial islands. Yeah, so some people are projects that are proposing to, instead of trying to build everything offshore, to actually create some onshore areas offshore and try to use that to bring to shore. And I'm sure, or I hope that you have heard about North Sea Wind Power Hub and all the activity around it related to building artificial islands and creating those hubs in the North Sea. So I think this is pretty much an open subject yet on how to do things best. And in my opinion, this graph sort of discusses what are the main challenges there, because it shows when should you choose which technology, and you can find that in all kind of shapes and forms. But I think it basically says that both AC or DC connection or technology have a capex cost, a fixed cost, an initial cost, the fixed one here, and then they have a cost which is variable and depends on the distance. And you can see that the way the technology behaves is very different. For the AC one, the slope of the variable cost, it's much more pronounced on the DC line, but the DC cost is more on the capital. It's much more expensive, the fixed cost, the converter's cost. So you can do that if you try to change the balance between those two and basically try to modify where this intersection point or the critical distance is. And I think today, what I was trying to show earlier, that there is a range in between for this critical distance where nobody really knows which one is the best solution yet. So you can try to make this slope, to bring this slope down. And there are some technically, I think you can do that by having low frequency AC type of transmissions coming from the railway station, or you can try to bring down the DC terminal cost. And my final example of our work today is related to that, and we are talking about different HVDC connection concepts. So today, this is the way, what I was showing you, the two converters, one the onshore and one the offshore converter, which is typically a voltage source converter. And this is what carries a big part of those initial costs today. So one of the proposals that we've been also working with is to replace this with a diode rectifier unit, and depending how you calculate that, this can result in cost reduction, significant cost reduction from this part. These are numbers coming from the industry, so I'm not gonna, please don't keep me responsible for that. But there is a potential for cost reduction by changing that. So why don't we do that? What is the main challenging in do that? So the main issue there is that the way they operate now, this offshore converter is the one in charge of creating the grid and creating the offshore voltage and frequency. And then the wind turbines, the only thing they have to do is connect to that network and then produce power. So the wind turbines in this context, we say they are grid following. So they simply have to match the AC grid voltage and frequency and operate like that. If we go to the proposed solution, the diode rectifier unit, this is a passive unit. So this unit has no controllability, so then they cannot create this network here offshore. So in this case, the wind turbines have to take this responsibility, and then they have to operate in what we call synchronous grid forming mode. So they will have to regulate themselves the AC frequency and AC voltage, and they have to do it in a synchronous way, because it's not only one unit like here that is doing so, operating in sort of a master slave, but this is distributed, so all of them have to work in tandem. And remember, we are talking about hundreds of wind turbines and hundreds of converters that have to do that. So this is a fundamentally different way of controlling your wind turbines. And then, of course, there is already work done in that. There are some solutions, and I think there is good potential to make this work. But then there are also challenges which are more practicality related, as the energization of the offshore wind power plant. Sorry for the typo. So as I said, if we have this is a passive unit, and this is only unidirectional. It only allows for the power to flow from offshore to the onshore, and that means most of the time that's fine. But you have a few times, like when you start up your wind turbine, your wind plant and wind turbines, then the energization path is the other way around. So by using a diode rectifier, this path cannot be used anymore. And of course, if you want to go to this kind of projects, you have to find a solution on how to energize your offshore wind power plant. And there are already some proposals, but what we are proposing there is what we think is one of the solutions with the lowest cost, is to actually connect the DC link of the transmission with the DC link of the wind turbines, and this is shown here, and use this path to energize the offshore wind farm through the wind turbines. And the preliminary results for that, it looks that is possible to, we can do that, and we think it's, yeah, from where we sit, we think it's a very smart idea to do that. But then, even if you solve this problem, we have to make sure that because of the added controllability or the added responsibilities you have on the wind turbines control, then we have to make sure that the wind power plants can provide the system services, and this is the system value that I was showing before. So we want to do that. We were looking at if they still can provide fast frequency response from offshore wind farms where they are connected through this system, and this maybe has a little more, makes a little more sense after the August event in the UK, where they had a partial blackout for different reasons. But in the future, they will expect that offshore wind power will actually contribute to provide the power and not be, part of the problem. So what we did here is try to look if we have this wind farm connected through the diode rectifier, if we can provide this wind farm active power control. So basically, when you have an imbalance in the system, you try to increase the power produced by the wind turbines. And if you want to do it very fast, of course, if the wind turbines are operating at maximum power, then you want to extract kinetic energy from the rotating masses. And this is not necessarily something new. It's been studied before, and it's some of the wind turbines say they can do that in practice, but we were looking how to do that with a diode rectifier. And then of course we try to do it in two ways, in non-adaptive and adaptive, because by slowing down your wind turbines you can provide the extra power in the initial part when you want it, but then the wind turbines will have to slow down when you release that control. They will slow down because they will try to bring back their balance. So then you will have what is called a second dip. So we are trying to minimize that by having more clever ways of controlling the wind turbines. And of course it works. That's why I'm showing it here. So you can see here briefly the results, and the black one, the adaptive one, is providing the support. So you have a smaller dip here, but it also avoids a second dip later in the response, in the timeline of the response. And that, of course, was wow result. So this is the third part. The third example I am presenting, and just wanted to tell you that because of time and because I didn't want to make anyone cry, I only presented selected results from only 3 of the works we are doing, but there are actually much more work that is happening behind that, and we have a lot of things like we are discussing about grid following. If you have grid forming wind turbines, then you can actually do other capabilities like black start or enhanced frequency control, or so if you try to control your cluster, you can try and do it better. So we are developing more and more, working on this direction of trying to reduce the cost of energy and increase the performance of the offshore wind farms. And I also put that here because this is work we are doing with in the group, and that brings me very nicely, I think, to the third part of who am I doing this work with, or with whom we are doing that. And I like this it's a little funny story, because the first time I saw this this proverb, you want to go fast, you go alone. If you want to go far, go together, was actually in the email signature of a person we contacted for a collaboration, and he answered he's too busy, he has to write a book and he has to do that fast, but he had that in his signature. But still, I think it's a very nice proverb, and I think it verbalizes very well what I believe, that the work we are doing, it's work we are doing in teams. And I always love to show this picture every time I get the chance, because I want to believe that back at RISO, when they started doing that, they somehow believed in that, because they decided to go together, and we get to what our department is more than 30 years later. So maybe not so fast, but still steadily. And yeah, if you're curious, I'm not in either of those pictures. In this one, for obvious reasons, I was just a kid, and here because I was not in our department meeting. But I think that one of our characteristics in our department is to work together. And of course, I'm in the coolest section from our department, the INP section, Integration and Planning. And I think we are world famous at RISO, at least for our appetite for getting together and having cakes. And actually, looking at this picture, I sort of realize why we have, how this appetite for cakes, it's impacting me. So honestly, I prefer this picture than this one, because I think, yeah, for one obvious volumetric reason, but also because I think you can see in this picture, or the big difference into this picture is that we have much more younger colleagues. So I think our section has also changed over time. I think when we started in 12, when we became a university department, we were a bunch of seniors and then a few young guys, but this has changed significantly over time, and now you can see a section that is very young. I would say the youngest in our department, but I don't really know. I never looked at it, but it feels like that, and I'm sort of proud of that, because I think I have contributed directly to that. And since my boss Carsten is not here today, I can say that was our merit. So I think we are, and even I look younger, surrounded by younger people. No, don't you think? I think so. But we do that in our section, and I think it's always very nice. There are very nice moments working with young colleagues. A lot of nice moments when they get recognition from their work, and we somehow also do that together with them. And we also have another colleague that finished and who actually provided us a fantastic photo opportunity. I don't see you. Where is Edgar? He's here. So I don't know why this is not on Instagram yet. Maybe somebody will do that at some point. But I personally enjoy very much the very relaxed atmosphere in Denmark, but from time to time it's also a lot of fun to try and see how would I look like if I lived 150 years ago, when we go to places with much more tradition and yeah, way of doing things. So nice times. And what I like about this section is that we are still crazy about wind. You see I don't know if you can see it, the picture is the wind turbine, and of course cakes. We have cakes all the time, but also we have a nice group that is doing activities outside, and maybe you can see what was the event, but I'm old enough to know when not to go to that, so I think I was very skillful in avoiding that event. So finally, I think we have a very nice work. But we also have, it's not only internally, but we have a large international group, and from time to time we also have some fun. Ferhat, maybe some of you remember, one of our former colleagues and a very good friend, but also relaxing times by myself, maybe way too relaxing, but yeah. And in general, you know, doing this kind of work we are doing, it's hard work. We have to have lunches outside. And by the way, actually, I have to say to my wife, this is not a wedding. It was actually a lunch in a project meeting, okay? And then we have to deal with the big challenges all the time. Yeah, even got lectures on the big challenges from time to time, and stay until the end and fight with the big challenges. I try not to do that so much anymore because of other reasons, but. I think it's always enjoyable, and we have good time working with our colleagues here, but also with our colleagues all over the world. Now, what next? So I think basically we will continue our work in making sure that we can integrate and bringing offshore wind to the shore in the best possible way. And actually, this is a very new thing that came out from an IE wind consultation, a very broad consultation, and I was very happy to see that when we look at the grand challenges in the science of wind energy, actually the third one, optimization and control of fleets of wind plants working synergistically within the power system, is spot on the work we are doing. So I think we have a lot of things to contribute to the grand challenges for wind energy. And of course, I do think that sooner or later we will start seeing this kind of offshore power plants, which will be based on different technology, maybe DC-based, maybe floating, maybe producing locally, have hydrogen locally, and so on. So the technology is developing, and we are working towards contributing to that development. And then I think the experience from working with offshore wind, can also be used in other places. So everybody is talking, or it's a lot of hype about 100% converter-based power systems or 100% RES systems. And then I think that actually what we learn from operating or doing research on this kind of setups is going to help this, because if you look at this setup, we have one converter here, and all of those are, every single wind turbine has only converters. So we are talking about 100% converter-based power system. And I know it's not exactly the same what we mean by the big topic, but I think a lot of the experience that we are developing and the knowledge we're developing here will fit very nicely in the development and the transition of the power system. And then, of course, continue our international collaboration. I think this might be a little maximal what I'm showing here, because that was from my application, so there I was trying to be a little maximal, but I do think that we are very international and we work with a lot of partners all over the world, and we are very, very involved in European research, and would like to continue this. And of course also work internally in our department and with the other departments, and we already do that today in a number of projects, mostly related to control or to optimization and optimal design of offshore wind farms. So we will continue to do that. And finally, on education, of course, because we are a university, I think maybe you have already realized that I'm personally very interested in PhD education, so I'll plan to continue this. And it was funny because we had this quote, or this was said by a person from industry very recently about the need of qualified personnel in the industry, and I think it's right. I think from time to time we suffer because we have challenges keeping our best people here. The industry keeps stealing them from us, but we keep insisting working with that. And of course, it's not only, if you want to do that, it's not only at the PhD level, but I think at all levels. So we are also we just started this year a course on offshore wind grid connection and integration, and of course continue education level on continuing education and the other levels. So, and by the way, I will try to make sure that this guy will also start paying for some of those PhDs if they are so interested in having so many PhDs. So we're planning to continue that. So finally, instead of having big conclusions or a lot of words about the future, I will just leave this here for a second. So this is what we are planning to do and continue doing that. And I think we can, and I think this is not just a vision. I do think that this is something that can happen. Thank you. No question.
Raising opportunity for asking questions. I would suggest that we skip that.
Sorry, guys.
Although there may be a subscript here and there that we could argue about.
Okay.
But congratulations.
Thank you very much. I think it's the. Thank you.
have refreshments where you can ask all kinds of questions to Nicholas outside. So
I need a drink. After a drink, yes, I can. Thank you.